Please join me in welcoming Nikita.
Thank you. Hello, my name is Nikita Tarakanov. I'm going to talk about automation of discovery vulnerabilities, of taint analysis, of BitBlaze. And before I kick off, I want to tell the story behind that work. It was 2010 year, and Alex with me, we're working in a CSS company, doing a lot of reverse engineering, source code audit, and because there are a lot of code, we thought that it will be a great idea to automate the process of vulnerability discovery. And at that moment, in my opinion, one framework was great. Actually, at the moment, it's great too. So let's kick it about the afters. So Alex is a security researcher from Ukraine. He's an organizer of DEF CON Ukraine group. By now, at the moment, he's sleeping, I think, because he is in California. And he works in the BitBlaze project. But this talk is not some secret stuff about BitBlaze, because this work was done almost a year ago when Alex was working with me. And actually, doing IT security business in Russia is kind of complicated, so we separated. He moved to US, I stayed in Russia. So about me, after we separated, I think Alex gave nice work in BitBlaze, but I doing reverse engineering myself. Right now I'm independent. Actually, I'm author of some articles in the IT Security Russian magazine. It's kind of the one magazine in Russia about IT security. And most of the time I like to reverse kernel land. And in recent years I discovered some vulnerabilities in kernel land on Windows platforms. And as me, Alex and me like to solve problem of automated reverse engineering. So this is actually talk about it. So the main I will talk about first of all about taint analysis theory itself, then about BitBlaze, because this system is based on BitBlaze with some enhancements. And next will be loss time. You're gonna see what's it. And next I am gonna talk about some pitfalls about actually taint analysis and about implementation of this approach, like pitfalls in BitBlaze and another pitfalls. And in conclusion, some results. So actually, such system has two parts. First one is a kind of static part. It's based on IDA. Actually, it's IDA and several plugins. For example, xrefing of some dangerous function like memory copy, malloc, but free memory, and there are a lot of analogs. So actually, a potential vulnerability, it can be every instruction that manipulates memory. For example, virtual memories, there is a move and there is an indirect call. So I will talk later about internals of some plugins, and kind of dynamic part, it's BitBlaze. And BitBlaze, just, when in 2010, in 2008 and 2009, here, firstly, BitBlaze project released Vine, and next they released Temu. But actually, the thing is that it's not a framework that it's ready to use in real world scenario, because it's kind of raw, and you have to enhance it a lot to get at least some results. So I will talk about theory. By the way, how you find vulnerabilities? By fuzzing, I think, right? Raise your hands. By fuzzing? By mutation? Okay. For example, what do you do if there is some undocumented protocol and there is some CRC or some crypto stuff, and actually by mutation fuzzing you simply get nothing. So you have to manually reverse engineer some unknown format, and this is takes a lot of time. And to solve some kind of problems in recent years, taint analysis was born. Actually, taint analysis is kind of data flow technique. So we get some first input data, we taint it, and then we monitor how instruction process this data and save and to log. It's kind of it's implemented by tracing, so it's kind of log file. I will show you how it looks like. So basically, source, it's like in real world, it could be anything: network packet, keyboard press, file from disk, or even you can taint output from some function, for example. You can taint address of malloc or something like that. So instructions processes data somehow, and next for example, if you have just 1 kilobyte file, and there is a, for example, zip file, and firstly code unzip this file. So you marked, for example, file with just offsets, and then program starts to unzip and some acting. So this taint information actually could be anything. In BitBlaze, there is a, for example, offset plus what kind of data. For example, does it come from a network or file? You can implement it whatever. So it's kind of flat model, and this is kind of chain. For example, move instruction from memory to registry, or so it's, if we're talking about tainting, there is objects, and object has some taint. It's kind of whatever you want. So once again, so okay, about static taint analysis. Actually, at the first part, using IDAPRO, you can reveal some potential vulnerabilities, for example, by looking for xrefs, but because it's just static without real values, it's has a lot of false positives, because you can't say in 100% reliable that this is vulnerability. You have to generate data that after when analyzing program processes data, you will go to this potential vulnerable place and some crash triggers. So it's kind of actually in real world static data analysis. It's you use it with dynamic. So they are in both. When they separate, it's just low effectively. And when you use it in a combination, this is good because by static, you can remove unuseful code. For example, if you look, there's just like no operation on memory, just some mathematics without some interesting instruction like indirect calls, indirect jumps, just some calculation. You just skip it and focus on interesting instructions like virtual functions, memory copy, calls, mallocs, and there are a lot of potential vulnerable places. So let's talk about framework, about BitBlaze actually. This kind of great framework, but in fact, open source version, it's very buggy. It's a lot of bugs, a lot of dirty hacks, and it has a lot of future, but you have manually coded because they release just small part of what they have actually. So this framework, you can use it not just for discovery vulnerability, but for a lot of things. For example, there was talk at Black Hat, and approach was, if you got crash from some kind of mutation, fuzzing, or protocol-based, you just have crash, and you have to analyze what's there. Is it exploitable or not? So Charlie Miller at Black Hat presented that using BitBlaze and taint analysis and taint propagation techniques, you can reduce time of analyzing in, for example, if you manually with debugger, actually it takes, for example, 12 hours, and with BitBlaze it takes minutes. So you just press the button and some algo says that this is memory corruption from this offset from the file. So BitBlaze consists of two main parts, Vine, which is kind of static component, and Timu, which is dynamic analysis component. And there are a lot of private stuff. They're closed, but there are a lot of papers, academic papers, you can read it. They're actually great. So the dynamic part, Timu, coded nice. It's based on Kimu, on fast emulator. And there is, because Kimu is just emulator, it's know nothing about process, about threads, about files. It just process instructions. So to know what to trace, where is the process, there is a semantic extractor. It in Windows, it's implemented by driver that set notification routines For example, if some process starts, it gets a message that this PID, this process started, and by some registered interruption, it sends some info to the host. So there is a communication between emulation guest, where there's some targeting software executing, and the host, where there's Vine and everything else. And the second, it's actually main, it's a taint analysis engine. So it's implemented by hooking each instruction and copy, for example, if it's move from registry to memory and registry is tainted, so it implements propagation. So we just copy tainted info, and there is a lot of actually code in there, because a lot of strange code, because x86 architecture has a lot of instructions, and if you take a look at Timu, it's just, you can see that there is a lot of functions with names like instructions, and there is got operands and just do some actions with taint info. And on top of that, there is an API. By using this API, you can code, you can develop a lot of interesting tools, like you can automatically do code unpacking, malware analysis, because this talk about vulnerabilities, I use tracing. So for me, it's interesting how analyzing program process some data, or how to trigger the crash in an automatic way. So there is a lot of APIs. For example, if there is a EIP got tainted, if there is some process started, it has a lot of interesting things. So basically, it's kind of virtual machine, but not virtual emulator. But because it's based on very old version, on version 0.9.1, it was released in, I think it was January 2008, and it's slow. It has a lot of bugs, and the main fact that Timu based on this version of Timu and not on the latest one, because in version of 0.10, developers of Timu made a lot of enhance of performance. They implemented tiny code generator, and after that, implementing taint propagation algo, they broke some functionality, and BitBlaze team, and actually when I see how tiny code generator, it's not clear how to implement taint propagation algo with tiny code generator. So maybe it's a good idea to get the latest version of Timu and remove somehow tiny code generator, so downgrade. But the thing is that the tiny code generator, it's kind of feature of Timu. So about Vine, it's so if we talking about Timu, it's just the main purpose. It's just trace everything. trace and log. If we talk about Wine, the main purpose behind Wine, it's his intermediate language. And if we're talking about tracing, the front end, for example, trace. And there is some utils which processes the trace file and generate IL program. And the thing that IL, intermediate language, the main idea behind implementing another intermediate language is to simplify, unify the code. So if we're talking about x86 architecture, its instructions are definitely not atomic. For example, X add instruction, it's addition and then exchange. It changed a lot of flags. So when you have such operations that influence a lot of objects, it's a good idea to simplify. And with this intermediate language, if you take a look, there are just 7 instructions, and actually the main of them, it's var, jump, cjump, and there is a 4 special command: hold, assert, label, special. So program is just a map between declaration and instructions. There is also expression, and the thing is that what is the nice thing behind this intermediate language? So you can transform trace from one architecture another architecture, because it's for example, it doesn't matter how memory works. It just has own process, and there's operations like plus, min, and minus, unary operations. Actually, there are some kind of types of values. For example, 1 bit, 8 bit, 16, and nice thing is that memory could represent Indian, big Indian, little Indian. It doesn't matter. So when you trace file, for example, with trace cap, and then process this trace file to see what actually instruction in there, you will see something like that. There's a address, instruction, it's ATT syntax, and before instruction, actually it's kind of taint info. So if we take a look, T0 means that statement is not tainted. T1 means that it has some taint info. So for example, in this instruction, repstos, we have EX, which is not tainted. There is a marked T0, and memory, which is has some tainted info, and actually, because it's not atomic instruction, there is a rep prefix, and rep uses counter register. So there is several objects. For example, register EAX, register ECX, memory at some address, and there is also, if you see RCW, there is some kind of info about how object used. So EX is just read. So basically, this instruction done value of EX reads and assigned to memory at address which equals EDI register. So after you can see that there is a some digits after T1, for example, 15 means that it comes from network, then 12, 31, it's, for example, offset, and you can implement a lot of your own taint info. So this info you got after trace reader, but it just for reading. Actually, the thing is to generate IL code from the trace file. And AppReplay actually does it. So this is kind of just using of application replay util. And when you set some input data, actually it means that it's kind of attacker controlled. So for the intermediate language, there are marks input, index, offset, and the type of the value. So this is kind of, for example, looks like intermediate language code. So there is a values, types, assignments. So the main thing behind free variables is to, you have some first trace which covers some functions, and at some function you have at some conditional jump you want to change, for example, change direction. So for this purpose, there is a WPU, weakest precondition utility in Vine package, and it from intermediate language it produces STP code, and STP is solver, constraint solver. This is not about BitBlaze, it's separate. Actually, it's STP, in my opinion, it's not the best one. There is also SMT from Microsoft Z3, but Vine and BitBlaze uses this. And for example, after WPUtil processes some file, it generates STP program. So STP actually, there is a own language, which is maybe more easier than Vine. And the main thing for solver, it's to solve something. And the trick that we have some trace, some intermediate language program, some STP program, and we change some condition on some jump and query it false and say give us counterexample. So the main idea is to, I haven't, to get there, tell me that I'm not true. So not on not, give us true, and this solve. So if we change some path and query that this STP program is false and give us counterexample, STP will produce some output. Output of STP is concrete values for free variables. So, for example, this answer of STP is that, yeah, invalid, and there is values for some kind of input values. So with after we generate second input data with these values, we can get another path in the program. So this is actually main parts of Vine, of Timu, and is, as I said before, BitBlaze, what is released in public, it's a kind of tool not ready for using in real world. To discover some vulnerabilities, you have to build your own hooks. For example, you have trace, monitor, some memory operations, and in Vine, for example, application replay, it's just replay program, and we have to change this utility to make changes to paths. So second is STPs, and either plugins. There's a plugin that just find X reference calls from calls to some allocators, string copy, memory copies. Actually, there are a lot of potential dangerous functions, and in direct calls, it's great for kind of profiling double free and user free and out of sight, out of bounds array vulnerabilities. And actually, we have a database where we store everything from either Pro plugins. And next, to process some program, to trace some program, we have to execute it. So we have to build publishers. Publishers is just a code that executes program with our input data, and actually iterators that loop whole process to get some results. So, for example, every program, it's a graph. There is a node, there is an edge. And for example, IDA Pro plugin said that in that node, for example, potential dangerous mem copy. And we have trace, we have path that near that. And the main purpose is to how to get to potential vulnerable place and trigger some bad things like memory corruption. So minimum goal is to maximum coverage dangerous code, and maximum goal is to coverage maximum all the code. But in reality, if you coverage 100%, it doesn't matter that you discovered every vulnerability, because there is a range of some objects, and on some not conditional branch, there is actually a branch because there is an operation on memory, and at this instruction, exception could be triggered, and you're going to redirect to exception handler. So basically, there is a kind of invisible path in the program. So maximum coverage of the all code, it from the static part, it's just static part doesn't see every picture, whole picture. So the basic algorithm behind that, it's first of all, we get a list from some nodes where is potential code. Then we, in Timo, in emulator, we invoke targeted code. For example, if we test in some, for example, Adobe Reader, publisher just invoke Adobe Reader with our PDF. Then tracing begins. At some point, we stop tracing, converts it to intermediate language. Then we change intermediate language to get closer to place where we're gonna analyze, where we have to go actually, and IL prime. Then by WPUtil we generate STP program prime, and after solving STP program prime, we get data. After processing, we will get a new path. So, and this is loop to point 2, and there is kind of there is no end in this algo because there is exit conditions. I haven't write about them. For example, exit condition if crashed, if you get crash, get EIP tainted, so you just see that some code doesn't connect to input data. So this is kind of visual representation. So we have some input data first. It processes in emulator, then Vine generates intermediate language. By the way, you can not just trace, you can do a lot of things. For example, hooking, profiling, and because Timo and Vine connects to each other, you have to build your own Vine-util, which is kind of not easy for me because Vine is developed in OCaml language. It's a functional programming language. It's kind of another blend for me. So after we get trace, we generate IL code, then we change path, and then we get a STP prime code. STP generates new input data. So this is kind of easy, straightforward idea, but actually it works because it works, but it has a lot of pitfalls. Well, I will talk about it later. Actually, the main disadvantage of this system is performance. And about performance and how to get rid of it, just for example, use this system for explore some path, not 100% of coverage, just some part of the code, and then you will have a lot of input data that each input data covers different path in program, and then you just mutate this data. And this approach, kind of a combination of mutation-based fuzzing and coveraging, gives really nice results. So disadvantages, like I said previously, it's performance, and actually definition of the vulnerability, it's not an easy task, because there is, for example, logical vulnerabilities, which actually I haven't thought how to define them. So if we're talking about performance and how it's awful, some digit overhead. In ideal world, there is a kind of 1,000 loss and in reality, it's tens of thousands, and actually, it depends on how much of functionality you have done in Timu, because by hooking a lot of functions, the overhead will grow very quick, and it depends on your target, because tracing a lot of some big programs like Google Chrome or another browser where there's a lot of threads. In Timu, it's just scary. For example, I tried to analyze some vulnerability in Microsoft Office, which I found recently, and actually generating, just tracing to the vulnerable code with actually data that crashed Microsoft Office takes about 40 minutes, and trace file is about 30 gigabytes. And when you have such a big trace file, IL program is huge too, and it's simply AppReplay simply can't process such huge files. So, in my opinion, it's this BitBlaze. It's not a good thing for userland programs. It just it's better use pin tools. There is some project called BAP. It's the same as BitBlaze, but it's Vine plus pin tools. So if you like to discover vulnerabilities in Chrome, Internet Explorer, or whatever userland program, it's better use BAP than Timu, because pin tools DBI is much faster than Timu. So there is also implementation issues in BitBlaze itself, because in Vine, Vine uses VX and Timu for logging instructions. It uses disassembler Z, and the thing is that some of the instructions VEX can't handle. For example, some special kernel length instruction. So it's because VEX is part of Valgrind for using for userland programs. And AppReplay, for example, utility, it's only generates intermediate language for a single thread. So it's basically for userland programs, it's not enough. You will not get some real results. So this system actually kind of concept, it's not, I would say, it's good only versus some part of codes. And in my research, I figure out that BitBlaze is better used for kernel length because there is less code, and traces are smaller, intermediate language programs smaller, everything smaller, and works faster than if you want to trace some userland program. But actually, even in kernel land, also performance is very bad. So about future of this system, it's reduce overhead of performance, and the bottleneck of this system definitely is Timu, and TIMU, which is based on QEMU. So the straightforward thought, it's we have to remove it somehow. For example, move algorithm of data propagation to hypervisor, and in my opinion, it will enhance performance a lot. But a lot of code to port, rewrite. There is some project Ether, which is based on Zen, but it kind of dead in my opinion, because it's about 4 years old and doesn't upgrading whatever. And next step, it's automation of exploit generation, because this system, it generates just proof of concepts, it just triggers a crash. And to automate exploit generation in real world, we are facing a lot of exploit mitigations, and to generate reliable exploit, you have to build some state. So for example, if we're talking about pool overflow, or in your land heap overflow, you have to defragment, fragment somehow. So for example, stack-based overflow, in my opinion, they just have gone in history, because there is a stack canary, and it's stack canary protection by now it's almost everywhere. But in fact, I have discovered some vulnerabilities, some antivirus. There is no stack canary in 2012. It's strange. And the main problem of automation exploit generation is that even if you get EIP tainted, EIP under your control, you know exact formula, how input data change EIP. It doesn't mean that you have exploit, because there is a randomization, and there is a hot topic on the internet, how to automate memory leakage to control EIP and know where some binary resides. So, in my opinion, it's if someone will solve it, he will be billionaire. So there's another thought how we can combine another frameworks with this system. For example, there is one good project, S2E. It's LVM plus QEMU, and it also uses STP. But the great thing is that it's based on a newest version of QEMU. It supports ARM architecture, and there is some kind of new concept that there is no point to between, if you have a trace file, there is no points to generate IL, STP. It's actually, this slide is Alex is more skillful in that, so I will skip it. Let's take a look about some kind of examples. For example, for kernel land, overflows, stack, pool, integer, pointer overrides, null pointer dereference, race conditions, and for example, various logical vulnerabilities also reside in kernels, and because there are a lot of types of logical vulnerabilities, it's hard to define them properly. So, for example, this is very common in programs. For example, there is a multiplication, then allocation of some size, and there is a loop, and there is a memory corruption in that loop. And on free or in that loop, there will be crash. So there is a, we can define by intermediate language how such vulnerabilities look like. For example, if we got two objects and they, after some operation, it can be multiplication, addition, concatenation, whatever. And then this var goes to allocation, doesn't matter heap or stack, just assignment, new variable, somehow it depends on range of the memory of the length, and there is a next, there is a addition on that memory, and picture the main purpose, the main question: if there is a variable bigger than total length, it looks like it's out of bounds, right? So, for example, it's of course it's basic definition, because in real world there is a lot of different examples, but the main thought it's like that. So, for example, actually, basically, yeah, we can define vulnerability if EIP get tainted, but also definition on pointers, buffer overflows, integer overflows, integer operation, and the results, because it's a lot of static parts of the system gives a lot of false positives, because it's kind of paranoid. It shows every instruction like LIA, load extension address, and multiplication, like it's a potential overflow. And to solve that it's not potential, it's real, you have to implement value analysis, value range, what object can give range from, is it constant or not, and for example, define race condition. Straightforward thing is just see if there is some place where the memory, some actions with memory, and is there a thread safe? And if it's not, it's potential, there is potential race conditions. So if we're talking about kernel land, for example, famous IOSTL, and let's take a look at device IO control. There are some parameters, and actually the concept behind it's taint IOSTL code, taint buffers, taint lengths, and see, for example, there's some thoughts. Firstly, we can taint only IOSTL code, not buffers, not lengths, just IOSTL codes, and see what exactly range of IOSTL codes some device processes. And then, only after that, we taint buffers and lengths to see if there is some range checks, if there is some memory corruptions, and actually for device IO control, there is two methods that if it's method buffered, you have to taint only data that you process to driver by invoking ISTL, and if ISTL code is method neither, it's better. It's great to taint pointer itself, because inter output manager of Windows just doesn't check the valid, is the pointer valid or not. So this is a basic concept, and actually this concept works. For example, in this 0 day, about 20-month old 0 day, the thing is that untrusted code, code from the user land goes to some function, FTL release context, but FTL release context was developed in that way that only kernel, only data from the kernel FTL release context process only in kernel land. And if you somehow have to access to such function from the user land, it's at first time it's decrement arbitrary memory, but then you wanna some coverage next code, and reveals that if you constrain some object, you have to control. You will lead to, it leads to control of EIP totally. So actually, the first one, decrement of arbitrary memory, it's already exploitable condition. But if you skip it, if you allocate memory, just decrement it, and process next, you will see that there you have total control of EIP register. And this very easy vulnerabilities migrated from one version of total GData, total kernel, total care to another. And in the newest version, it's finally fixed. Also, coverage and smart hooking of some interesting functions reveals strange realization of some defenses. For example, unprivileged user can simply turn off or firewall. It's and decrease security of the whole system. And the thing is that in it, ISTL, there's two vulnerabilities. One is just BSOD, null pointer dereference on reading, and after crash after null pointer dereference, there is just a logical vulnerability. Then a great example of mistakes in kernel land that, in fact, Agnitum, it's one of the firewall and antivirus very famous in Russia, but they bought some engine, and this engine, actually it's file vb-enc-nt.sys, it's kind of DLL, but in kernel land. And the thing is that in this DLL, there are about 50 expert functions, but the picture is that you can invoke these functions from the user land, and these functions, a lot of parameters are pointers, and there is a full trust on them because it's a DLL in kernel land, and no checks for valid memory. So it will it simply it leads to 50 different vulnerabilities like arbitrary memory read, arbitrary memory write, and full pawnage. And the thing is that this buggy code used by over several products, over 7, 8. Actually, it's a product of Virus Buster, if you heard about it, I don't know. And next, when I tested the system, I revealed some interesting examples in Microsoft code. For example, they still haven't documented some interesting functionalities in input-output manager of Windows. For example, method buffered I call it signal, because if you process ISTL with 0 lengths and 0 pointers, it will craft IRP and processes to driver. And actually, this leads to a lot of stupid BSOD bugs. Actually, this signal is if we're talking about CA internet security, there is about 4 vulnerabilities of this kind. Then, okay. Okay. If we see another example, some code just reboot emulator. There's on several ISTL, there's a full corruptions. So you can discover just in one particular product, which basically decreases security of your system by implementing new functionality. And the thing is that, like in this example, that one driver using by several products, the same thing with this, because this driver as BREDRF.sys also present in Unthread and Lavasoft. So actually about Trend Micro, I already talked at Hakito in Paris. Actually, also there is another device with stupid vulnerability. So the main pitfalls of taint analysis is that there is some problems, for example, with Trolan, which is, for example, you have data tainted, and Trolan calculates length of the string by subtracting the pointers. Data are tainted, but pointers are not, and there is no taint information, nothing propagates. Also, fall of taint analysis, it's constant values propagation, and if you can solve all these problems, but if you enhance levels of taint information, it's more overhead. And yeah, about some pitfalls of taint in kernel land, there is also taint information lost. Then you have, for example, a check of some system variables, which is you haven't control. For example, just previous mode. Some code checks if it's come from kernel and from user, and it's a variable of process state, and you haven't tainted, you haven't see anything. So it's and some pitfalls. For example, there is a defense mechanism because when you tainting, it's low, very slow. There is a great performance overhead, and there is some mechanism that if some process doing something in graphic, it just blue screen. So we'll get nothing. So about pitfalls about ISTL, as I said, it's checking of system variables, for example, getting of previous mode, or some check of is it process our antivirus engine or its attacker, and some of the antiviruses even implemented hooking this function and just close the vector in ISTL. So, in conclusion, I think that quality it's kind of security level. Taint analysis it's not it's a kind of technique of the main time, but in main time it's mostly from academia, and most of the people get rewarded by using more simple solutions like stupid fuzzers, like mutation-based. But this approach, nice that it's just full automation. You haven't to build your own fuzzer all the time. So, and conclusion about Microsoft, that actually it's strange that a lot of drivers which are signed, and in that driver there are a lot of stupid vulnerabilities. Because it seems that Microsoft just signed and doesn't check. It's strange. So that's it. I'm Herbert.
Peter, thanks a lot for your talk.
Yeah.
We're already past the entire official.
Uh-huh.
So if you have any questions, you can talk to Peter, but there's also dinner, and I'm sure he will answer. Thanks.
Okay.